The coldest spot in the known universe isn't in the depths of the Boomerang Nebula, it's inside this gold-plated cylinder in a laboratory in Zurich. When we think of the void of space, we imagine a frozen wasteland. And to be fair, at roughly 2.7 Kelvin, the cosmic microwave background radiation makes outer space pretty miserable. But for the engineers building the future of computation, 2.7 Kelvin is practically tropical. It is far too loud, too energetic, and too chaotic. To unlock the power of the quantum realm, we have to go deeper. We have to push matter to the very edge of stillness. We need to reach temperatures where the vibration of atoms almost entirely stops. We are talking about 10 millikelvin. That is 0.01 degrees above absolute zero. At this temperature, we aren't just fighting the weather, we are fighting the fundamental laws of thermodynamics. This is the story of the dilution refrigerator. It is a masterpiece of quantum engineering, a mechanical fortress built to protect a few fragile qubits from the heat of a universe that is constantly trying to shake them apart. It is not magic. It is the most sophisticated plumbing system ever designed by humanity. To understand why we need to build these massive gold-plated chandeliers, we first have to understand the enemy, heat. In our everyday world, heat is just energy. It's what makes your coffee steam and your laptop fan spin. But in the world of quantum computing, heat is noise. Quantum bits, or qubits, are the heart of a quantum computer. Unlike the bits in your phone, which are either a 1 or a 0, qubits exist in a state of superposition. They are incredibly sensitive. Even the tiniest amount of thermal energy, the slight vibration of a nearby molecule, can cause a qubit to lose its state. This is called decoherence. If a qubit gets hit by a single photon of infrared radiation, the calculation is over. The data is corrupted. To a qubit, a room at 25 degrees Celsius is a chaotic inferno. Even the vacuum of space is too noisy. To make a quantum computer work, we must create an environment of absolute thermal silence. We need a place where entropy goes to die. This is why cryogenics is the backbone of the quantum revolution. We aren't just cooling things down for the sake of it. We are building a sanctuary. But you can't just use a bigger version of your kitchen fridge to get to absolute zero. Your kitchen fridge uses a vapor compression cycle. It relies on evaporating a refrigerant to soak up heat. But as you approach absolute zero, standard gases turn into liquids, and liquids turn into solids. The physics of cold changes, and so must our engineering. When you see a photo of a quantum computer, you're usually not looking at the computer itself. You're looking at the cooling transition system, the dilution refrigerator. It looks like a high-tech steampunk chandelier, shimmering in gold. Why gold? It isn't for aesthetics. Gold is an excellent thermal conductor, and crucially, it does not oxidize. In a vacuum, at temperatures near absolute zero, any layer of oxidation or rust would act as a thermal insulator, trapping heat inside the components. Every plate, every bolt, and every coaxial cable is plated in high-purity gold to ensure that heat can be wicked away with maximum efficiency. The structure is divided into stages. As you move from the top plate to the bottom, the temperature drops exponentially. Each stage is separated by thermal shields, cylindrical vacuum cans that act like a Russian nesting doll. These shields reflect infrared radiation back out, ensuring that the innermost core is shielded from the heat of the room, which, relatively speaking, is glowing like a sun. At the top, we start at room temperature, 300 Kelvin. The first stage uses a pulse tube cryocooler to get us down to about 4 Kelvin. This is the temperature of liquid helium. For most of the history of science, 4 Kelvin was the finish line. It was the coldest we could get. But for a modern 1000 qubit processor, 4 Kelvin is still a roaring fire. To get to the millikelvin range, we have to stop using mechanical pumps and start using the strange properties of quantum liquids. This is where we enter the realm of dilution refrigeration. To go below 1 Kelvin, we rely on a very specific, very expensive trick involving 2 isotopes of helium, helium-4 and helium-3. Helium-4 is what you find in party balloons. It's common. Helium-3, however, is incredibly rare on Earth. It's often harvested from decaying nuclear weapons or proposed as a reason to mine the moon. When you mix these 2 isotopes and cool them below 0.8 Kelvin, something strange happens. They undergo a phase separation. Imagine oil and water. They don't want to mix, so they form 2 distinct layers. In a dilution refrigerator, the top layer is rich in helium-3, and the bottom layer is a mixture of mostly helium-4 with a little bit of helium-3 diluted into it. This happens in a component called the mixing chamber. This is the heart of the machine. To create cooling, we use a pump to pull helium-3 atoms out of the bottom diluted layer. Because the physics of the system wants to maintain a specific concentration, helium-3 atoms from the top pure layer are forced to cross the boundary into the bottom layer to replace the ones we pulled out. As these helium-3 atoms cross that boundary, they undergo a process similar to evaporation. Just as water evaporating off your skin takes heat with it and cools you down, helium-3 crossing this phase boundary absorbs thermal energy from its surroundings. This is quantum evaporation. Because this process doesn't rely on a gas, it can continue to work all the way down to temperatures that would freeze any other substance solid. This is how we reach 0.01 Kelvin.
Reaching the temperature is only half the battle. The other half is talking to the computer. A quantum computer needs to be controlled by microwave pulses sent from a room temperature room. This creates a massive engineering contradiction. To control the qubits, we need to run wires, specifically coaxial cables, from the 300 Kelvin top plate all the way down to the 10 millikelvin bottom plate. But wires are made of metal, and metal conducts heat. If you used standard copper wires, the heat from the outside world would travel down the wire like a fuse, instantly frying the qubits. To solve this, quantum engineers use superconducting cables made of materials like niobium titanium. These cables are designed to have extremely low thermal conductivity while still carrying the high-frequency signals needed to manipulate quantum states. Along the way, the signals have to pass through attenuators and filters. These components serve two purposes. They move the signal, but they also quench any thermal noise. We have to strip away the heat from the signal itself, so that by the time the microwave pulse reaches the qubit, it is cold signal. Every single screw, every wire, and every junction is a potential heat leak. In a dilution refrigerator, a leak the size of a microscopic pinprick is a catastrophic failure. The vacuum must be more perfect than the vacuum of space. The isolation must be absolute. This isn't just a fridge, it's a high-performance engine where the output isn't motion, but silence.
As we stand here in 2026, the scale of quantum engineering is shifting. We are moving away from prototype systems with the dozens of qubits to massive systems with thousands. This presents a new challenge. The chandelier can only get so big. We are now seeing the rise of large-scale cryogenics. Instead of one fridge for one chip, engineers are designing entire rooms that act as cryostats. We are seeing the integration of cryogenic CMOS, control electronics that can actually live inside the fridge at 4 Kelvin, reducing the number of wires that need to go all the way to the room temperature world. We are also seeing advancements in how we source helium-3. With the demand for quantum computing skyrocketing, the supply chain for these isotopes has become a matter of national security and intense industrial interest. The quest for the coldest temperature has moved from a laboratory curiosity to a global race for computational supremacy. Why do we do all of this? Why spend millions of dollars and thousands of engineering hours to reach a temperature that shouldn't exist in nature? Because at 10 millikelvin, the rules of the universe change. Physics becomes pluggable. We can simulate new materials, crack encryption that would take a classical supercomputer billions of years to solve, and understand the very fabric of molecular biology. The dilution refrigerator is a testament to what we can achieve when we stop trying to fight nature and start using its most extreme edges to our advantage. It is a machine that creates a void, a pocket of stillness in a vibrating universe. It is the coldest place in the universe, and it is where the future is being built, 1 millikelvin at a time. It's not magic, it's thermodynamics pushed to its absolute limit. It's the art of the cold. Thank you for watching this deep dive into the engineering of the absolute zero. If you want to understand more about the mechanical and digital systems that define our world, make sure to follow Not Magic. No illusions, just engineering.